This is 4.1.1, part 2, free body diagrams. So we'll start with what a free body diagram is and how they're drawn. A free body diagram shows us the object and all the forces that act on it. Shows the object and all forces acting on it. If it's in equilibrium, then all of the forces, the sum of all the forces, will equal to 0. Now, you've got types of forces, contact forces and non-contact forces. So our contact forces these are forces that act when two bodies have to be in contact with each other, have to interact with each other directly. So these are examples such as friction, which we label as FR. Friction acts parallel to the surface and in the opposite direction to the motion of an object. So parallel to surface and opposite direction to motion. Friction can still act even if an object is not in motion, but an object is attempting to move. For example, if we pretend that friction disappeared, would that object move? If the answer is yes, that object will move if friction were to disappear, then in which direction does the object try to move? And friction acts in the opposite to that direction. Then we've got the normal reaction. Or that acts 90 degrees to the surface or perpendicular to the surface. And this would be in such a direction that it stops the object from falling through that surface. So gravity tries to pull things down. If the object is on a surface, that surface puts an equal reaction force upwards to prevent that from falling through the surface. Then we've got tension. Tension acts in strings and pulleys. And often is used as a way of transferring a force from one body to another. And sometimes tension is also used to transfer forces from one dimension to another dimension. So from vertically to horizontally, for example. Next, you've got contact forces that act in fluids. So contact forces in fluids, these are things like drag, and these are things like viscous forces. Fluids talk about liquids and gases. So often when we say the word fluid, students default to thinking that we're talking about liquids only, but something that's a fluid just means that particles can move around. So both liquids and gases have particles that can move around. So liquids and gases. And here we're talking about drag and viscous forces. Drag always opposes motion, similar to friction, and it comes about because the motion of the object causes the object to collide with particles in the air or particles in a liquid, putting an equal and opposite force. So this opposes motion. And viscous forces are how sticky the substance is. Now in reality, there are actually no such thing as contact forces, because all these examples of contact forces are some manifestation of one of the four fundamental forces in nature. Your strong nuclear force, your weak nuclear force, gravitational, or electromagnetic. But in the macroscopic world and Newtonian mechanics, we can think of these as contact forces. So now we move on to our non-contact forces. So these act on the center of mass of different bodies, but they don't need to be in direct contact with each other. So here we've got gravitational, which is always attractive. And acts on masses. You've got electromagnetic, which has two simplified variations, which is the electrostatic forces or magnetic forces. Electrostatic acts on electrically charged objects. Magnetic affects magnetic objects or moving charges, because moving charges have their own magnetic fields. And then you've got the strong nuclear force and weak nuclear force, but in mechanics, these two are basically not needed. Okay, let's move on. Start a new page. Let's do some examples. So if we have an aeroplane moving at constant velocity, Now, if our airplane is moving at constant velocity, it means that it's not falling, even though it has weight. So it must have a force that's equal and opposite direction to its weight. So this is the lift. So we've got weight acting down, and in equal and opposite direction, so the arrow has to be approximately the same size when you're drawing it. We've got our lift. Then you've got the thrust of the plane going forwards, but it's not accelerating forwards. It's at constant velocity. So you have an equal but opposite force, which is drag, backwards. Okay, another example is pulling a sleigh. So if we have a cable that's pulling the sleigh, we've got tension in that cable pulling it forwards. If we're moving at constant velocity, so the sleigh's not accelerating, then there's friction on that sleigh acting in the opposite direction with equal magnitude. And then we do the obvious ones. Everything has a weight, so our sleigh has a weight going down. And it's not falling through the floor. So there's a normal reaction from the floor on that sleigh acting upwards, equal and opposite. Next, we're going to look at resolving vectors in 2 dimensions. So on a new page, let's write a new title, Resolving Vectors. So let's say we have a force that's acting diagonally, so it's acting in 2 dimensions, at some angle, theta. That force can be separated into 2 component forces. And notice I'm drawing the component forces in a different color. And there's angle theta from the horizontal. So if you use trigonometry, SOHCAHTOA, you'll find that cos theta is opposite over hypotenuse. And sine theta is adjacent over hypotenuse. So let's write these down. So we'll label these as our x and y components. So we've got cos theta is equal to y, x over h, and sine theta is y over H. And in this case, H is just the force. So we'll label that as F. So now, if we wanted to separate this force F into its components in the x and y directions, we say that x is equal to F cos theta and y is equal to F sine theta. Put a box around those. Let's do an example. So we've got a force of 100 newtons acting from the horizontal at 30 degrees. So in this case, the horizontal component is going to be F, x is equal to F cos theta. So x is equal to 100 cos 30, which is equal to 87 newtons. And y is equal to F sine theta. So y equals to F sine 30. And F is 100. Let's put 100 in there. So y is equal to 50 newtons. And then you can verify that it's correct, because if you did the Pythagoras of these two values we calculated, we should get 100 newtons again as a resultant force. Another example is a picture frame, which is a little bit more complicated. So imagine we have a picture frame or some object which is hung on a wall using two strings. And both these strings have equal tension. And we've got 5 degrees from the horizontal. The question will require you to find the tension in each string. Now, each of those strings contributes some upwards vertical force. They also each contribute some horizontal force. Now, the string on the left will contribute a horizontal force pulling to the right, but the picture frame is not moving to the right. The string on the right is contributing a horizontal force to the left. So their horizontal components cancel each other out. And the sum of their vertical components add up to equal to the weight of the picture frame. So step 1 is to separate the two strings. And a way that I like to visualize it is I like to draw it again, but this time separate the two strings out so they're not touching each other. And that makes it easier to see what happens. there's our tension in each of those. Now in red, I'm going to draw their components. Five degrees there. And 5 degrees there. So each one of these has an X component and a Y component, like so. Now the picture frame itself has weight trying to pull it down, which is mg. So mg down. Okay, let's take each of those strings with their tensions and separate them into two force triangles. So tension and tension. So in each of these cases, y is equal to t sine 5, and y equals to t sine 5. And both of these two forces are holding up the picture frame vertically. So t sine 5 plus another t sine 5 is equal to mg. So sum of upwards forces equals to the downwards force, which is weight. So 2t sine 5 is equal to mg. In this case, the mass was 3, so it's 3 times g. So if we want to now find the tension in each string, tension is equal to 3g over 2 sine 5. And that gives us 170 newtons. If we wanted to then find the horizontal component on each string, x, we'll take our tension and say that x is equal to t cos theta. So x is equal to 170 cos 5. Now cos 0 is 1, cos 5 is almost 1. And so we should get a number that's close to 170. So x is equal to about 169 newtons. So what's interesting here is that most of the force that the strings are feeling are due to the angle at which it's been hanged. And most of it is acting in the horizontal directions, rather than the vertical that you'd normally expect. All right, let's move on to forces on an inclined plane. Start a new page. Let's first draw our inclined plane. So this is our inclined plane in blue, and we're going to draw a box or some object sitting on that plane. And we're going to say that this box is not sliding. It's not sliding down. And then we're going to start by labeling the forces and then figure out what these forces are. So, first of all, label the forces that are obvious. And the first force is the box has a weight. And weight acts vertically down towards the ground. So I'm going to draw weight, mg. The box is sitting on a surface, so it's also got a normal reaction because it's not falling through the surface. And that normal reaction is perpendicular to the surface. So we'll draw a normal reaction. Which is perpendicular to the surface. Now use your imagination. Is that box falling? Well, I said no. It's not sliding, it's not moving. So that means it must have some force stopping it from doing that. Well, which force opposes motion on a surface? Friction. So we've got friction acting opposite to the surface, so opposite to the motion. We expect it to slide down. So friction will be acting up the slope. Now looking at this, you don't see any forces that try to slide that box down the slope. But intuitively you know, if I were to make friction disappear, that box is going to slide down the slope. Now, what's actually happening is weight is acting down. But directly below that box is a surface at some angle. That causes the weight to split into two components. A component of a force which is parallel to the plane to slide it down, and a component of that weight which is perpendicular to the plane to keep it touching the plane. So the weight is causing the box to slide to the left, but also slide down so that it's always touching the plane. And it's doing that simultaneously. So in a different color, I'm going to draw those forces. So let's make them red. So these two forces only exist because of weight, which means that they're smaller than weight. And if I took these two red forces and I did Pythagoras, then I would get mg. So let's label these. So this is the parallel component of weight. And this is the perpendicular component. Right, I'm going to carry on. So, the weight causes two things to happen. It keeps the box on the plane, and it also causes the box to slide down the plane. Let's write this down. So weight causes the box to remain on the plane and slide down the plane. So next I'm going to draw these forces in a force triangle to help you visualize it. So we're going to draw our inclined plane as a dotted line. And then we need to draw our two forces, our two red forces. And we draw them in such a way that they make a force triangle, which then is equal to our weight. This is where a lot of students will slip up, because they will draw these arrows as I've drawn them in the first diagram, which is acting at the center of mass of our box. But when you're doing a force triangle or a vector triangle, where you end one vector is where you begin the next vector. And that's going to make more sense when it comes to resolving the weight into its components. So let's do that. So let's start from the top of our inclined plane, and we'll do our parallel component first. So here's our parallel component drawn. Then we're going to draw our perpendicular component. And then the mg will just connect the start and end positions. So it'll be vertically down. Now I've drawn these arrows a bit too large, so I'm going to make the first one a bit smaller. So we can draw the first one again. So let's draw it from here to there. And then mg goes there. So we've got here mg, we've got the parallel and perpendicular. So far so good. And our angle here. Now, if we analyze this triangle, we can see that the angle on the top would be 90 minus theta. So if the top angle there is 90 minus theta, and these two red forces are perpendicular to each other, then this angle down here must be theta. Which means that the parallel force is equal to mg sine theta, and the perpendicular is equal to mg cos theta. Put a box around that. Now, if that box is not moving, that means that friction is equal in magnitude to our parallel force. If box is not moving, then friction is equal to mg sine theta. So there is no resultant force parallel to the plane. And at all times, the normal reaction from the plane is equal to the perpendicular component of the weight, and that's at all times. At all times, and I'll put in brackets, unless box is lifted, R equals to mg cos theta. And that's the end of 4.1.1.